Hello. How's everybody doing out there? Saturn, how's it going? We are looking at some samples in the SEM. So these are some samples from June Lake, California, which is a site that I've been working on for a couple of years now. And this diatom that's right here is one that I actually described as a new species. So it's one of the dominant diatoms in this community, and at least in the fossil record. And like I said, I've been working here for a few years on these things, and I have a graduate student, Laura, who started working on this, doing some work with us on this project this semester, and she's going out into the field in June, hopefully, to collect some more material from a different lake that's basically adjacent to June Lake called Gull Lake, and that will be part of her master's thesis. So we've been looking through the June Lake slides in SEM so that she could kind of get familiar with it and the taxa that are present. So I've just been sort of was on slides, on stubs already, so low amount of preparation on my part. So in the light microscope this week, we've been looking at some diatoms, and I would say that you can see a lot more detail in the SEM than you ever could in a light microscope. We haven't been looking at them under the best conditions for the light microscope either. Those are samples that aren't prepared. They're wet. The diatoms are still alive, whereas these are prepared stubs from prepared samples, and the diatom skeletons are all we see because it's in the scanning electron microscope. So, hey, Pragmatic, how's it going? I'm doing well. I mean, I saw most of you guys last night, right? So, hasn't been that long. It's been a while since we've done an SEM stream. I've done a bunch of light microscope streams in the last week. I just on Wednesdays for the past couple of weeks been on the SEM, in part just because of some scheduling issues with the Dr. Mo's stuff, and in part just because the semester's kind of winding down a bit, but pretty soon we'll be on a new schedule for the summer, and it could be all over the place. We could have SEM time regularly, as I'm working with some students on projects this summer, and many of them will be on the SEM. So if they feel like streaming, we may be streaming some of their work on the SEM as we go. It should be pretty fun. So I'm going to zoom out so you can get a sense of the material that we're looking at. So this is all the way out at our current height. Below me, there's a picture of what's going on inside the SEM. The little stubs are in the camera over here are what we're looking at, and you can see the surface is just covered with diatoms. And you get a totally different view in the SEM because we can get a lot closer. So this is roughly the magnification we were looking at them when we were looking at them in the light microscope last night. So they just look like little dots and sticks and whatever at this elevation. But one of the nice things about the scanning electron microscope is that we can just zoom in and keep zooming in, and it doesn't have lenses in the sense of a light microscope. So our magnification is just whatever elevation we stop at. And so right now we're at 6,000 times magnification. The highest magnification on my light microscope is 1,000 times. And even the best light microscopes don't have more than 1,000 times magnification, really. You can blow up the image by making the eyepieces bigger, but it's not the same as actually making the sample. So it's the objectives that sort of control the magnification. The eyepieces just sort of control the enlargement of them. And at a certain point, you just start enlarging stuff. You're not actually increasing the resolution. So it's like you could take an image and project it onto a wall with an overhead projector. It doesn't make it, makes it bigger. It doesn't necessarily make it better. This is the outside. That's the, hang on. These are the Rafi. On this diatom right here, the Rafi runs around the outside margin. I'm just actually trying to tweak the focus a little bit. To improve the image quality. And I'm going to rebalance the brightness here in a second as well. This usually takes a minute or so while it figures out the brightness and contrast. I usually let it do the brightness contrast settings because the SEM computer software is actually pretty good at figuring out the balance between brightness and contrast. It does, at least initially, a better job than a lot faster than I would do it. So this is the area I was kind of focused in on to try to get a better image. Just trying to improve our image quality. What I did was I adjusted the beam intensity, which is basically equivalent to the spot size or the area of the surface that's being hit by the beam. And the smaller that area is, basically, the higher, more resolved your image is, but it sends a little bit less information back because, the size of the beam basically is a little bit finer. And unless you slow down the beam, basically increase the density of points that it's collecting, it just makes a lower, a dimmer image. But it also allows you to see a lot more detail. So I often will bounce around between 7 and 10 on my instrument to try to figure out sort of a good balance between resolution and brightness. So usually when I zoom out, look at an overview, I want it to be a little bit brighter so I can see everything. And when I zoom in, I want a lot more detail so I can actually get it in focus clearer. And you can see that trade-off now as we sort of zoom out. It's a little bit dimmer, and you can't see as much detail as a result because there's fewer points returning information, basically. But it's also less blended. So everything we see on here is, or almost everything we see on here is diatoms, except that's a pollen grain right there. That's pine pollen. So if you're suffering from allergies, this is the bad guy. Saturn asks, how are the samples for the SEM prepared? Which is a question we get pretty regularly in the channel. these samples were prepared by taking the initial mud sample from a lake. So if you just like scoop some mud out of the bottom of a lake, as the first step, we would try to get rid of all the organic matter so that just the silica part is left behind. And that is done by adding hydrogen peroxide at concentrations of like 30% or 35%. So what you get in the pharmacy when you go to the store is usually 3%, so it's about 10 times more concentrated than that. And it acts as an oxidizer, which means that if there's carbon in the sample, it donates oxygen to it and makes carbon monoxide, and then usually immediately after that, carbon dioxide. And both carbon monoxide and carbon dioxide are gases. So think of all the carbon material that's in the sample basically becoming a gas. And then we do this in a hood. So all that material basically goes out into the environment as carbon dioxide. And what's left behind in most cases is just the silica. So silica doesn't react with oxygen very much. It already has oxygen in its chemical structure. And that allows us to basically just have, usually just diatoms are left at that point then. But there's also some other things. So I said pollen. Sometimes the pollen will basically make it through the processing. It shouldn't, but it does. This sporopollenin, which is what pollen is made out of, is highly resistant to a lot of things. And if I left it in there for a long time, oxygen would cause it to break down. There are some other things that are in here that aren't diatoms. For example, this thing right here. Hang on, I'm going to improve the image quality in a second, so don't panic if it looks a little grainy. That's so I can move around, basically. And then when I want the image quality to improve, I just slow down the beam, which increases the density of points and gives us more information. So this thing right here that we're seeing with all the little spikes coming off of it is a piece of a sponge spicule. And thank you for the follow, Roger. So all of the silica, if there's dirt, just like silt-sized fractions of clay or quartz silt, those particles will remain in the sample, and then the diatoms, sponges, sometimes pollen, sometimes a little bit of the green algae like Pediastrum and Cenodesmus, and they have like a little bit more resistant material sometimes, or Botryococcus. So I do get some other algae besides diatoms occasionally, but they're usually highly degraded. And then chrysophytes, which are also have a silica skeleton, chrysophyte scales and cysts, stomatocysts, and the skeletons of things like ostracods would be still around after that processing. They're relatively low abundance in these samples because they were collected in deep water. But also we sometimes see things like butterfly scales or I'm trying to think of some other random things. Phytoliths, sponge spicules, anything that's a little bit more resistant that's not made out of mostly carbon, like, organic carbon. Inorganic carbon usually isn't affected. So if it's calcium carbonate, we'll still see it. And sometimes we'll treat the samples with hydrogen peroxide and hydrochloric acid, or sometimes the hydrogen peroxide doesn't do enough removal of material, and so we'll also do like nitric acid, which will get rid of all of the organic matter. It's a little bit more aggressive. So I try not to do that unless I have to, or if I want to make the samples really clean for SEM analysis. So hydrogen peroxide usually doesn't get everything as well unless you leave it in there for a really long time. Anyway, then once that's done, we sort of rinse it a few times and get rid of the any sort of waste material that's in there from that byproduct of that reaction and get rid of all the oxidizers and acids and anything else that we put into it. So it's just water and diatoms and then whatever else is in the sample. And that extract is then added to a cover slip to make a diatom microscope slide, or onto one of these little stubs that you see sort of down below me here, these little cylinders. And we just put that material directly onto the cylinder and let it dry. So it just air dries basically. And as a result, it's stuck on that surface. So we can take that sample that's been digested and all the organic material's been removed and all that's left are, diatoms and some other fragments usually. And then those little stubs that you see, the cylinders that are below me, they're about 10 millimeters tall and about 12.5 millimeters wide. So they're very small. I'll try to get one for you for a second so you can get a sense of it. So like that's my finger next to one of them. I don't have giant hands, but there's a pencil. Maybe you're more familiar with scale. So they're pretty small, and the part that we're looking at on here is just a little tiny area on the surface of one of these, the very top circle part. And then I don't know if you can see it very well, but they have like a gold cast to them, and that's because we also then will take this thing, put it in the sputter coater, and it puts a layer of gold over top of it, everything. And that makes it a little bit more conductive, so that when we put it in the SEM, silica, which is usually a poor conductor for electricity, will charge up if you don't do that. And so the particles will start to glow after a while, because the electrons will sort of get stuck on it. But if we coat it with gold, basically it can get to the ground easier, and then basically it won't sit on the surface of the diatom, causing it to glow. And I mentioned Chrysophytes stomaticis earlier, and I found one here. That's why I stopped on it. I'll give you an example of one of those. So they just look like little orbs, basically, like Christmas tree ornaments is what I usually call them for people. It's this thing right here. And when we zoom in and look at it, you'll see that it's basically, they're not always this boring. This one's pretty boring. Sometimes they have all kinds of bumps and ridges and spines and things on them. This one's just a simple sphere, and then at one end it has an opening right here. It's like a Christmas tree ornament does. That's why I sort of relate them to those. And this is where the organism goes in and out. This is the aperture, or opercula if you like. And I think usually there's something sealing these closed to keep things out, but it's basically how chrysophytes don't look like this. This is the cysted stage, and they do this basically to overwinter, or the conditions in the lake or something they don't like, for example. That's how they live. Finally noticed my channel after seeing you with the plankton lady all those times. Well, Roger, the plankton lady and I are good friends, and she usually is here as my moderator, but I think right now she's getting her second COVID vaccine. So if it's not right now, it's probably pretty soon. But she might be here soon. Hope my day is going well. Hello, Shafard. Things are going well, as far as I know. I'm on the SEM, so how bad could they be? Wing the ultimate nug. Is that an opening? Is it hollow? Yes. Just like a Christmas ornament, basically the inside is the sort of part where the organism insists or rests during the winter season, and then it crawls back out that hole somehow. But I think they're mostly hollow inside, and the reason that I say that is in the light microscope, when you look at them, you can actually see the internal ring of silica, like the open space that's in there. Because a light microscope, the type that I use is a transmitted light microscope, so the light actually passes through things in order for you to see it. Hey, Devil and Mrs. J. it actually passes through it, so that allows you to see what's on the inside, basically. And because we digested it, there's nothing on the inside, right? So it's just hollow internally. But they're pretty rigid, so they don't break very easily, which is one nice thing about them. And they're a little bit... sometimes the skeleton is a little bit thicker than diatoms. Diatoms are pretty lacy skeletons with these sort of highly ornamented holes and other structures on them. And as a result, they tend to dissolve a little bit more quickly and break a little bit more easily. A lot of their structure is reinforced by internal ribs and things, but it still is pretty easy to break a diatom relative to like a crucifite. So more commonly we see diatoms broken than cruciphites. So most of the things that we're seeing in this field of view, here I'll slow it down a little bit so you can kind of see, to give you some idea, like these are mostly plankton. That's a crucifite cyst. But these little round guys are mostly plankton. And these ones are Lindavia intermedia. These ones, this one right here is a Stephanodiscus. All these ones with the cool spines on them. So I'll take a look at those in a second. And this one here is also a Stephanodiscus. These are all plankton. The sort of round ones most commonly are plankton and diatoms. And then these stick things you're seeing are mostly broken sponge spicules. And then the thing that looks sort of like a Q-tip is also plankton. And it's because the sample was collected in relatively deep water. It's mostly plankton. This little stick-shaped thing is also a diatom that's plankton. And then this one here is a Pinularia. That's a benthic diatom. They live in shallow water, but they can be carried into the deeper water areas by wave energy or something like that. So I'm going to scoot around until, I guess maybe we could stop on one of these, and I can zoom in and show you. This is a Stephanodiscus. Some of them are in better condition than others. This one's not in really great condition, so I'm going to maybe scoot around more and see if I can find a different one. But this is the external view. All those spines stick out from the outside of the diatom, like on the outside. So when you see a whole bunch of spines surrounding the outside edge of a Stephanodiscus diatom, it tells you you're looking at the outside. In the SEM, we might also see the inside. In my model, there's nothing there, but in the real diatoms, there's actually an internal and an external view. I'm going to see if I can find a really nice example for us. You can see when I change the brightness settings, what happens. So here's a Stephanodiscus on the inside. Here's a Stephanodiscus on the outside view in this field of view. And I'm just going to zoom in on the outside view here for a second and see if this one's in good shape. It's got a little bit of clay on it. But you can see all the little holes that are on the external part. And this one also is kind of raggedy, so maybe we'll move on and look for another one. But you can see these spines around the outside edge are really common for, well, characteristic for the genus Stephanodiscus. And that one's not a spine. That one is a external expression of the Rimiportula, which is one of the characteristic features of centric diatoms, and some other things. But so let's see if we can find some really nice examples, though. There's another external view of a Stephanodiscus. Here's an internal view. Right here you can see, if I zoom in, you see the spines are all pointed downward. And so we could actually come in and look at the inside of the diatom in this setting. Diatoms are always, or almost always, covered with a series of little holes like this, and little holes in this case are areoli for most of them. That's just the term that we use to describe these little radiating holes that are covered on the inside by a little plate of silica called a cribra. And then these ones are special structures. These are special pores called mantophotoportula. Sorry, these are central photoportula. And they have that name because they're just an opening with some satellite pores, some pores around the outside edge of them. So these have two little pores that are adjacent to them with coverings over them, and then a central tube, and that makes up the middle part of it. And they're a common diatom structure. The mantle photoportulas are over here, and the rim of portula is this one. So we'll get some better views of those eventually. The spines themselves don't have an internal expression, so those little features that you're seeing are actually below the spines down here. Let's take a look at that. It's sometimes hard to get a grasp of the features and what you're seeing unless you can kind of get an edge-on view like this. But these are the spines on the outside, and they're not met with anything on the inside because they're just ornamentation. They're just structures that are growing from the surface outward. These other things that are present, like this one, you can see that the external expression has an internal expression as well. Same thing with this one. There's an internal and external expression. And same with this one. There's an internal and an external expression. This is a rim of portula. It's sort of like shaped like a pair of lips, but on the outside a tube in this diatom. And there's a hole that actually passes through all the way through the valve or the cell wall. And then these ones are mantophotoportula that are going around. And there's a tube that goes, well, actually several tubes that go through the cell wall here. So what you see on the inside is matched by something on the outside. The spines themselves don't have structures like that. They're just external, and they're solid silica. They're not tubes or holes. So, but this is a nice view that lets you sort of see basically inside and outside at the same time, because we're right along the edge of this definite discus. So you can see that here. And then these things have external expressions, but they're just thickenings, little thickenings. They're not actually tubes. We can come up here and look at some of these spines. Actually, I could probably use this to help get my stigmation a little bit better. While we're here, if I need to. What do the spines function? Increasing surface area or defense? We don't really know. People give different explanations for why they have spines, and there's sort of like a laundry list of things people suggest, but I don't buy most of them. My interpretation of them, well, people will say they're for defense. Not that they necessarily make the diatom like, I mean, their skeletons are hard, so the spines aren't really like, I mean, it's not like they're ramming into things. Potentially, if something swallowed it having spines might make it like less palatable. But people usually say, oh, the spines make them bigger, right? So expanding the spines makes their size bigger. And because a lot of things in the, in the world, in this sort of world that the diatoms live in, if you're small enough to go in something's mouth, you go in its mouth. So if you add some spines, basically it makes you a little bit bigger. Again, I don't really buy that as an explanation, because how much bigger does this diatom really get by having spines around one end? Not very much. So, I mean, those spines are tiny, and they hardly do anything, right? So I don't really buy that that's a a great defense mechanism. I mean, it's possible it makes itself just a little bit bigger, but I feel like the amount of silica that must be invested in order to accomplish it isn't really matched by the amount of defense that's gained by making yourself like a half of a micron bigger. You're not likely to, being a half micron bigger is not going to make it so you can't be consumed. So I don't know. It's a question that I don't think we have really great answers for. In a paper that one of my students and I put out recently, we analyzed the diatoms by he made 3D models of them in AutoCAD. He measured all of the little parts, the holes, the processes, the pores, everything, and then reconstructed them in AutoCAD. And what we found was that they actually invest a lot of silica into the spines. A surprising amount goes into it relative to the rest of the volume of silica that they use. And the bigger the diatom gets, the more the volume of silica increases. So it actually has a really high cost with respect to nutrient requirements, right? So if you're an organism that's adding a bunch of silica, and silica is one of your nutrients that you need, there's a high cost with putting spines in. And so, I mean, the question of why they have them is, it's a really deep question in a lot of ways that I don't think we have great answers for. Let's take a look at one of these not round diatoms. Let's see how it looks. This is a navicula, and I can tell that because of the areolae, the openings, the striae, are composed of little holes. These sort of stripes that are on here are composed of little holes, and you can see them very clearly when I slow it down, hopefully. And they're sort of slot-shaped, right, rather than being rounded. They're these little tiny slits, and there's a whole bunch of them, and they line up to make things that we call striae, which are characteristic features of diatoms. And the fact that the pores are slot-shaped is usually one of the characteristics of the, it's not the only characteristic, but it's one of the main characteristics of the genus Navicula, stricto, the strict version of Navicula. In the light microscope views, I was talking a little bit about this structure, which is the Rafi that they use to crawl around or attach to substrates. And these structures that you're seeing here, the areolae and the striae, we don't know exactly what they do, but they're probably mostly for communication with the outside world. So not like a telephone, but rather exuding waste and pulling in nutrients. And then there may be some relationship between them and the chloroplasts as well. For some of the diatoms, they've observed like a higher frequency of chloroplasts near the actual openings. But that's not always the case, for sure. So let's move around and see what else we can find. So we've been sort of off in this just one side of the slide. As I mentioned, the entire width of the stub that we're looking at is 12.5 millimeters, the surface area on the top of it. And the field of view is always present down here. So you can see we have a 1.43 millimeter field of view, and there's always a scale bar at the bottom here as well. So Unlike my light microscope, it's got a built-in scale. As we change scales, it'll tell you the magnification over here, and the view field, like how big is our view field. It'll also tell you the depth of focus, so how much Z motion we have. And this SEM actually has a carousel that holds 7 different stubs. So if we wanted to, we could jump over to another stub, for example. You can see it's spinning down there, and take a look at some different, samples. I like to prepare them in advance and have a whole bunch on there. That way, if I can't find something on one stub, we might be able to find it on another. Or if we're looking to identify or describe diatoms, and sometimes it's a hunting game, trying to find them. You have to look around a lot of material sometimes to find the diatoms that you're looking for. And so can be challenging, and having the access to just sort of flip through multiple stubs is nice. So we're zoomed way out because I'm just trying to look for some different types of diatoms. There's these really big Stephanodiscus diatoms that are here. These are Stephanodiscus niagara, and then there's these large Cirrella diatoms here as well, we can see. And it looks like a piece of plant material is in this one, which basically made it through the processing. So you see some little fibers occasionally too. Those are probably plant material rather than plastics. But there may be some plastics in here as well. It's hard to tell without a color context. So we can't tell what's translucent or transparent anymore because everything's been gold coated, and we don't have light. We're just using electrons to see by. So let's zoom in and take a look at this diatom here. This is now we would call it Cirrella, but just relatively recently it was in the genus Semmetopleura. It just got moved or combined for a while, and it may be reseparated later. This is an internal view. We're looking at the inside of the diatom. And again, there's little holes on the surface, which is really characteristic for diatoms. And I'm going to try to tweak that view just a little bit, but maybe I don't have to. When I jump over to 7 beam intensity, things just improve enough that I feel like I don't need to work on it anymore. But it's also darker, so yeah, it could be something with the way that fluid flow goes around it. I've thought about that Saturn as a explanation. Maybe they use them so that when they fall through the water column, they have a greater tendency to align in a direction they want to be in. I don't know. Yes, navicula is Latin for small ship. It's like a little canoe or a boat. Hey, Micah, how's it going? Are you lurking while you're working? Is that what's going on? Thanks for dropping in. I'm fighting with the image quality a little bit. It's been a while since I used the SEM at a really high magnification. I've been mostly using it to look at pollen grains and stuff, which we could look at super low resolution, and for a couple of weeks now. And so when I put these samples on for the first time, I was like, ugh. The qualities of the image was not good, and I don't know if that's partly because other people use the SEM and I haven't used it in a while. but it was really out of whack. Like, column needed adjustment. The stigmation was all way off. The wobble was way off. So I spent a while fixing it before the stream started, and still feel like it could be better, but I usually feel that way, so that's just normal. It's just how I interact with the SEM. Doesn't matter how good it looks to everybody else. I always feel like it could be a little bit better than it is. But we can still see a lot of great detail. This is epithemia. It's either Sorex or Smithy eye. They have really intricate pores, so, and also we can look right in on the Rafi of this diatom. Their Rafi doesn't run through the middle. They have what's called a circumferential Rafi, and that means it runs along the outside edge, or the circumference. And still a little grainy. As you can see, they have sort of intricate, this is charging a little bit as well, really intricate pores. You have a navicular bone in each foot? I didn't know that. Hey, Magic Mr. Postman. You know, if you like the stream, you should follow it. But yeah, we look at some pretty cool stuff in here. I've been mostly doing light microscope streaming for the last couple of days, and I probably will again tonight. But on Wednesdays and sometimes on Saturdays or Mondays, I will stream from the SEM. So we're looking at very small stuff. Magnifications ranging between 100 times to about 100,000 times magnification. So, and to my knowledge, I'm the only SEM streamer on Twitch. So we look at a lot of cool stuff, though, mostly microorganisms. So welcome in. Trying to make some adjustments to the image quality. Also, thanks for the squad message out there, Micah. Yeah, thanks for hanging out, Saturn. We'll be looking at stuff from the SEM pretty regularly still. Ferox, hi. Steve Mendel, can I identify the difference between pores and the areolae? It's not clear to me. That's actually two words that mean the same thing for Steve. The pores, that's just a way of saying an opening. And so technically, let me give you an example. I need to find some, like, something with an apical pore field. So give me a second, and I'll see if I can find a gomphanema, or something with an apical pore field in our materials. This might be a bit of a snark hunt, because I don't know how common they are in these samples. They're pretty uncommon usually in deep water samples. And I might need to jump over to a different... I almost had one. This is a Cymbella. Here we go. So, typically, these holes that are a little bit larger are referred to as pores or areolae. And in some languages, or some scientists will also call them puncta, they're just basically little openings. And so the word pore just means any kind of opening. And these would be distinguished by the fact that they form stria, or rows. So you can see there's a row of them here, and a row of them here, and a row of them here. It gets a little chaotic on this end of the diatom, where the rows start and end. But it's a little bit clearer if we were to move into the middle here. So you can see they're shaped, in this case, as slots. So this is what we refer to as lineolate. In other words, they're little lines. And the little lines of areolae line up into making striae, which are separated by costae, or ribs, which is the structure that's a little bit brighter right here. So the dark areas are where there's no silica on the backside, and the light areas are where there's a little bit thicker silica in the diatom skeleton. So on the inside, these bright areas that you're seeing would be rib structures, or costae. And the darker areas would mean there's just one layer of silica there. So we can interpret this zone as a thin layer of silica, and these bands that are on either side of it as being thicker layers of silica. And then the openings themselves have no brightness because they're holes. So these are what we would usually refer to as areolae or punctae, and they're a type of pore, right? And then if we were to zoom down to the other end, on the very end of this cymbella is an apical pore field. So you can see it here. There's a whole bunch of little pores, slightly out of focus, because we're at beam intensity 10. So hang on. We're in the really small. I need to make the beam smaller, and I need to make some adjustments to make that work right. So give me a second. But there's a little field of pores down here, which we call an apical pore field, because it's actually on the apex, or the high end of the diatom. You see all these little holes down here. They have a different structure and position than the areolae. So they're still pores, but they're not arranged in rows. They're a field, a bunch of little holes all together with just a little bit of silica between each one. And they're not usually in like simple rows or whatever. But they do count as pores, so they're just an opening that goes through. This structure that we're seeing right here is the Rafi. So this is an actual slit that goes all the way through the skeleton, and so that structure is the Rafi, and this is the terminal Rafi end, which is deflected in this case towards the dorsal side. So if I were to zoom out, which I will here in a second for you, on the diatom that we've been looking at, this one, it actually is sort of banana shaped. You can see the rows of areolae or striae right here, and then the striae come all the way around, and here is the Rafi structure running through it. And the Rafi has a proximal end as well, typically, where it creates a little end point, and then we have the rest of the diatom. So if I zoom out, you can see the whole thing here is sort of banana shaped, symmetrical, and it has striae and areolae, and then the pores are any sort of opening that goes through it. Now, these would be contrasted against, like if we were to zoom in and take a look at this guy. To see all the little holes on the structure of this, they look like bumps because on the inside they have a pore covering called a cribra, and all the little holes are lined up in rows. So these would count as areoli, right? Same thing as here. All these little ones are lined up in rows. So stria or areoli, or in these cases, they're called fascicles because it's a different genus. But they're bundles of little rows of areoli, and they get thicker, or they have more holes as we get towards the outside edge because they're pie wedge shaped, right? So little pie wedges rather than straight single rows. But they are what we would consider to be areoli, right? Still areoli. So for the genus Stephanodiscus, which is what this belongs to, it also has these little openings, which are Remiportula, and then these little openings, which are here around the outside edge. These are Mantiphotoportula, and both of those are types of pores. In other words, they're an opening that goes all the way through the skeleton, it comes out on the outside. But they have different sort of characteristics which allow us to separate them from the pores, which are the areoli, right? So pore is sort of a broad term, and the detailed term like areoli is a specific type of pore. Also, the Mantiphotoportula is a specific type, a Remiportula is a specific type, the central photoportula is a specific type. There's all kinds of different types of pores, but its terms mean basically the same thing, just an opening that goes all the way through the cell wall. Good question. Hello, Bingo Beta Blocker and the Sicilian. I'm glad you like it. Yeah, a lot of the technical details in the language of diatoms is it requires a lot of like sort of a lot of careful distinctions. And so let me jump over to another sample, and I want to see if I can find some good examples of valve face photoportula for us. You can see it's a little bit out of focus because whenever you move from one stub to another, there's really minor differences in height, and so it's like it takes it out of focus, and it also changes all the brightness as a result. I gotta fix it. It's painfully out of focus to me, but it helps if I can zoom in on stuff. There we go. Let's fix the brightness now. There we go. So earlier I was talking a little bit about the spines and the areoli. These have fascicles and interfascicles instead of striae, but it's the same general idea. But if we look closely at Stephanodiscus, which is what this thing is, the characteristics of particularly the position of the features that I was talking about, really give us a way of characterizing the genus. So if you're trying to figure out like what are the characteristics that make something Stephanodiscus, there's actually like a specific subset of things that become really important with respect to knowing those different terms. So all Stephanodiscus have spines, these things right here, these big clunky things that you see here that are solid, cone-shaped usually, and they occur for Stephanodiscus at the junction between the valve face and the mantle, which is like on a bottle cap, the part that would wrap around the bottle. So the valve face would be the flat part, or it doesn't necessarily need to be flat, but usually the flatter part. And then the mantle is the part that's sort of the shoulder that curls under and around. And so, like the shape of the diatom is this way. It's the thumb parts in my diagram. And it's always going to occur right on the boundary between the valve face and the mantle. And this thing, which runs out to the spine, is the interfascicle, or costi, if you'd like. And they always occur on costi. So you can see that happening. Not every costi, rather, but everywhere there's a spine, it occurs on a costi, right? It has to. So structurally, that's where they place them, is on a costi, on the mantle, well, on the junction between the mantle and the valve face. And then, for staphylococcus, in order to make sure that you have staphylococcus, the costi ends at the spine, or at least at the interface with the mantophotoportula, which is this structure. So you can see these little bumps out here. They are also on a costi, and they occur below the spines, or more towards the outside edge than the spines. So here's a spine, and there's a mantophotoportula opening. There's a spine here, and there's a mantophotoportula hiding right behind it right there. There's a spine here, and there's one back here we can't see. This one we can see. There would normally have been a spine right here. We can actually see that there's a little bit of a silica patch right there where the spine used to be, but it popped off. And spines can break off of diatoms pretty easily because they're ornamentation. So there's a little patch right there where there's no areolae, but that where a spine would normally have attached, and it broke off. And it allows us to see that the mantophotoportula are down here, right? And the costi ends at the mantophotoportula. So the spines will sit on the mantophotoportula, and then it ends right at the mantophotoportula. If this were Cyclostephanos, the costi would continue past these, all the way to the edge of the valve. And then this structure right here, so this is the row where the spines are. This is the row where the mantophotoportula are. They're all at the same elevation. With each other. The spines are all at the same elevation. The mantophotoportula are all at the same elevation. This thing's at a different elevation. In other words, there's a spine. Outside of the row of spines, there's this thing, and then outside of this thing is a row of mantophotoportula. And that's because this is the external expression of the labiate process. And it's a different type of pore, and it's at a different elevation than the other features. But this is where it goes with Staphylococcus. It belongs between the spines and the mantophotoportula, and usually it's a lot closer to where the spines are in terms of elevation. Sometimes it's hard to even tell that it's recessed from the spine elevation, or it's basically at the level of the spines and it replaces one of them. But the mantophotoportula are always subtending the spines, so they're always farther below them on the outside edge or the outside ring of the diatom. So this combination, having fascicles, in other words, rows of areolae, interlinked with interfascicles between them, or costi between them, with spines, with a costi, spines on the end of costi, not every costi, but on where there's a spine, it's on a costi, and they are subtended by mantophotoportula. And I would say in some species the mantophotoportula can be more abundant. There can be more mantophotoportula than spines, for example, but not the other way around. If you have a spine, there's always going to be a mantophotoportula under it. And then the presence of rhizoportula. And those combination of characters is Staphylococcus. So like if you're trying to learn diatom taxonomy, it's really important that you know like all of these little terms and where those features are. And but the thing is, like, you can get it seems like a lot of detail, it seems like a crazy level of detail for understanding, but if you look at enough of them, it gets to the point where you just recognize all the features immediately. Like you just glance at it and go, oh, that's Staphylococcus, because you can see the ring of spines, you can see the fascicles and interfascicles very easily. You can see that the costi don't expand past the mantophotoportula to the outside edge. Boom, Staphylococcus. there's only a few things you could confuse it with. And so it's sort of like, I try to teach people you can't memorize every species. What you memorize are the features that separate one thing from another, right? Understand the concept, because genus is a concept. And if you understand the concept, then you immediately know that thing belongs to this genus or it doesn't. The only time when that becomes really problematic for any organisms is when you have stuff that fits into a genus but not perfectly. And then you have some extreme members of a genus, and then what do you do with them? So, are they just sort of circus freaks? Are they just things that are on the outside edge as an extreme version of that? Hasn't quite evolved into something new? Or is it actually a new genus? That's actually problematic. And a lot of times it comes down to splitting hairs between things to separate them. So, but once you can learn the terminology and what, there's just a set of maybe 4 or 5 characters that I explained. But you could know those 4 or 5 characters, and then anytime you came across that diatom, you'd be like, oh, this is Stephanodiscus. It has these things, even if you'd never seen it before. And that's the sort of skill, that you need to develop. So we're looking at the outside features of Stephanodiscus. You can see all the same features on the inside, except for the spines aren't visible because spines are ornamentation. But you can also see they have these structures on the valve face, which are the valve face photoportula. And valve face photoportula are extremely important when you're trying to figure out what species you're looking at. They're not particularly important for knowing that you're looking at the genus Stephanodiscus. So I'm going to tweak this, which is our beam intensity. And that's actually pretty good. And if I slow that down, we ought to be able to... You can kind of see the little pores on the cribra, which are the coverings over the areolae. Just a little dark. But really that's sort of how I function when I'm learning, a new species, because there's so many species of diatoms, it's impossible to memorize all of them. But it's easy to figure out if something belongs into a genus if you just have that little set of characteristics that you get used to recognizing. You can very easily become adapted to the point where you can identify something to genus very quickly. And I think most of my undergraduate students can learn to identify things to genus pretty easily. Just a little bit of training to get them to the point where they can make that list to know what characteristics they need to see in order to classify stuff. And you don't need an SEM to see most of those features. For some of them you do, but a lot of them, like the costi, are visible even in the light microscope, and so you can see them without the SEM. You can still tell what you're looking at to genus pretty easily. So let's say distinguishing it between things that are kind of close, like Cyclostephanos or some of the things that have been split off from Stephanodiscus, you might want an SEM, or you might need an SEM for those. But generally speaking, for most things, you probably don't need the SEM to actually get it into genus. To get it to species, you would for sure need an SEM for a lot of it, though, because you need to be able to see the number of valve face photoportula, which you really can't see in a light microscope at all. So I've been blathering for a while. Can I recommend a basic paper or text that has different bits labeled diatoms for dummies? hang on a second, Clay. You can just go to diatoms.org. It's in that link right there. And if you click on it and you click on any genus on that web page, it will actually highlight for you the key characteristics. So any of the genera, like if we were to go to Staphylococcus, for example, and take a look at it, there's a guide, and the guide shows you the characteristics that you need. Rate on the actual website. So there's those 5 characteristics I was talking about: striae radially arranged into fascicles, spines at the valve face mantle junction. The valve face is flat or conjunctionally undulate. I didn't really talk about that, but it's not important. Marginal spines may be subtended by marginal photoportula. You can see those highlighted in their pictures. And then rheumoportular, basically at the level of the spines, although I would actually argue they're usually slightly below them. But those are the characteristics that will let you get it into Staphylococcus, for example. The problem with that website is that they don't have every genus known to man on there, and in fact, there's a paucity of marine genera in there. Which is why when I'm looking at Pacific Plankton stuff, she sends me samples, or I'm looking at it on her stream, I can't figure out what genus it is, because I'm not a marine diatomist. I'm a freshwater diatomist, and I've only learned the freshwater diatom characteristics. And that website is the people that are behind it are the ones that I learned diatoms from. So I know all of the freshwater genera pretty well, but don't know the marine ones. And there's just some genera that they've never included on there, and it's a hole in the web page. But that web page is it's crowdsourced. So I think that Pacific Plankton and her friend Anna or somebody is working on filling in some of those holes and getting some of the marine genera on there, which I think is a giant hole in the web page, because there's a bunch of stuff in there I never learned, and I don't know what they are. I took a course in marine diatom taxonomy when I was a PhD student in Nebraska from Dave Harwood. But his focus was mostly on Antarctic marine-centric diatoms. And so, but it was also from 20 years ago. So a lot of the genera have changed names since then, or they've been reconceptualized, which creates a problem for me, because I don't know the modern names for a lot of things, and I don't keep up on the marine literature. So I usually am just like, oh, it's like Sordathalassiocyra or Sortocasinodiscus, but I usually need help from some of my marine taxonomy friends when it comes to the marine diatoms, because they're very different groups. Sorry, I'm just kind of looking around right now. I haven't really taken any pictures today. I just sort of went on a fun tangents on how to identify diatoms. So for clay, what we're looking at is these are diatoms. And where on the screen does it say magnification? Down here at the bottom, that's in microns. And then magnification of this from like a lens point of view is listed over here. I think you can see that when I do that, right? Yeah. So on the right hand side, there's a thing that tells you the magnification at all times, and also the field of view, like the width of the field of view. at all times. So, and the scale bar at the bottom will give you an immediate snap view, or this field of view down here tells you the width and height of the field of view in microns usually. So there are 1,000 microns in a millimeter. And so we're way below the millimeter scale for the most part. Our working distance is in millimeter. And if I zoom way out to the minimum magnification, like this, you'll see the scale bar is in millimeters. So that is the farthest I can move out at this height. And our entire field of view is 2 millimeters, which are the smallest ticks on a metric scale bar for a ruler. If you're not familiar with using millimeters, depending on where you're from, I might be explaining obvious things to you. Yeah, so the diatoms are really tiny, and part of the reason why we're looking at them in the SEM is that they're so small, basically. But one of the things that's cool about the SEM is it doesn't have fixed magnification heights. So right now our magnification is 137 times, but I can just tweak this little wheel and you can watch the magnification go up to 475. So we're not at like a typical microscope where the lenses have fixed intervals. We just keep zooming, and the more we zoom, the closer we get to something. As long as you can still focus it, you have the magnification. So we'll zoom in and look at this thing, which is a Lindavia intermedia, a diatom. And I will focus it for us. And now we're at 5,000 times magnification. So normal light microscope stops at about 1,000 times magnification, just to give you some idea. But that's not anywhere near the limit of our magnification on this machine. So you'll see the scale bars now say 5 microns across the bottom, and we can still get this in focus pretty well. Just need to tweak it a little bit. And now we're looking with 5 microns magnification, scale bar, sorry, and the magnification is 16,000 times. And if I want to just zoom in and look at this pore, for example, this is the external expression of a labiate process on the inside. I can also get that into pretty good focus. It starts to get a little blurry because I'm using a beam intensity 10, and I can switch my beam intensity down to 7, and suddenly everything is back into being highly resolved because I made the beam smaller. So our resolution's a lot higher. And then I can just keep zooming in. Now we're at 82,000 times magnification, and I can still get a resolvable image. So 82,000 times magnification is like 1,000 times light microscope magnification is the maximum. We're 82 times higher magnification than that, right? So that's the power of the SEM, is it does not use light. It uses electrons to see, and so we are, looking at everything at the wavelength of light is really the limit for its ability to resolve images. And the wavelength of light that we usually see, visible light spectrum, is 400 to 700 nanometers. And the wavelength for an electron is like less than half of a nanometer. So the resolution is way, way higher, and allows us to get crazily high resolved, high magnification images out as a result using an SEM. It's also why the image is in black and white, because there's no color. It's using brightness is being determined by whether or not objects are sort of facing the sensor. In other words, topography sort of determines the brightness and darkness of settings. Yes, everything is coated in gold in the scanning electron microscope right now, because diatoms are made out of silica. So their cell walls are not conductive, and therefore we have to we have to use some sort of a gold sputter coat over top of them. So is it all digital? Well, I mean, the images are all digital, yes, because it's the SEM's here, and the computer that's reading the information is next to it, and so we only see things in a digital expression. Hang on, and I'll sort of explain it to you a little better. This is a chrysophyte cyst, not a diatom. I just want to find something pretty to stop and take a picture of, and then and then I'll show you while it's taking a picture how the SEM works a little bit better, if you're interested. Everything here has got a little bit of clay on it, but I think I can still get this into focus. So it's got kind of like a clay haze over top of it. Let's jump over to 3, see what's on it. Sample is particularly dense, but I think it has a lot of pretty views on it. So let's get away from the middle where everything is sort of clumped together. Sample is jumping a little bit, I think because it's on top of a pile of stuff. It's actually moving from the beam hitting it. This is Lindavia oscillata. It's a little dark, but resolvable. So I'm just making some adjustments to it on the fly. I think it will be okay. Alright, it's gonna take a couple of minutes to take a picture. While it's doing that, I can try to explain this a little bit better. It's not evening, Mallory. Let's see. This is the SEM. It has an electron gun at the top. There's an anode, which is a positive charge. It pulls the electrons down from the gun into a beam, which is focused by magnets, through the backscatter detector, which we have actually extracted at the moment, onto the sample. And then electrons from the specimen basically are scattered off of the surface, but this has a positive charge, and it pulls the electrons towards it. So just like a flashlight bouncing off of a subject and then hitting your eye, it functions a lot of the same way as light would. Areas on the back side of this ant would be dark. Areas on the front side of the ant that are closer towards the sensor would have more bright aspects to it. And so the topography of the ant becomes visible, basically, as a three-dimensional object. And it's all done with electrons. There's no light in there. It's not taking a picture. It's drawing a picture. What it does is it scans over the surface line by line, basically collecting electrons from each point. It is saved to my desktop. It's hotkeyed, actually. This is F2, and this is F3. But they're a way for us to basically capture the electrons by having a photosensor as they bounce off or out of the sample onto the photosensor. It basically, the more electrons that hit it, the brighter it is, and fewer electrons hit it make it dimmer, basically. So all of our bright areas are areas where there's a lot of electrons coming back to the sensor. It's weird. It's like in focus here and then out of focus on the outside edge. It's just a little bit warped. Not a great view. I'm gonna just scrap that photo. Okay, so that's basically how it works. It's a simplified version of how the SEM works. Tweak some settings. I'm still kind of unhappy with the image quality right now. I don't know why it's just subpar. Something I've got to tweak a little bit better on here. Some of the samples are just loaded up with diatoms, like these ones. These are the boring kinds of Symbopleura. Just have simple openings. Some of the Symbopleura have really crazy pores that look like pictograms or it's epithemia, Stephanodiscus. Some of these Stephanodiscus pores are pretty interesting. This one's slightly dissolved, so you can sort of see through the surface a bit. Let's see if this actually turns into a little bit better picture. Struggling to get the brightness and contrast setting right. Looks like maybe the struggle was worth it, though. That's looking pretty sharp. Let's take that picture. This little Stephanodiscus. Hey, Henry. How you doing? So is this microchip tech? No, these are diatoms we're looking at. They're a type of algae that create a siliceous skeleton, and this is a sample from June Lake. Bacteria on the sample would be invisible. Snooze, we've seen bacteria, yeah, as Mallory mentioned. Everything on the sample is coated in gold, and it makes everything visible. In fact, any sort of material that's on it would be more visible here than it would be in pretty much any other format that you can imagine for bacteria. So SEM images of bacteria are probably the only images you've ever seen of them. So they don't conduct electricity, but the reason we don't see bacteria in these samples is because I processed them and it got rid of all the organic matter. So we're just looking at silica-based things for the most part because bacteria don't manage to make it through oxidation and digestion processes that we use. I don't have any microplastics that I've actually seen that I've identified in these samples. These are diatoms that we're looking at, Henry. But I've seen some things that I thought were plastic. It's really hard to tell in the SEM whether something is plastic or not because you can't see through it. You can only see topography, basically. So Mallory's helping out. Thank you, Mallory. Most of the stuff that you see is just, yeah, clay or schmutz. It would have to have been on the sample before they were coated, and that's the problem, Snooze, is that I don't want to see bacteria. I want to see diatoms because that's what I analyze. And so we decomposed all of the bacteria by adding an oxidizer, turned all of their carbon into carbon dioxide, and then they're gone. So our samples are sterile. And in fact, it got rid of everything that's organic in the samples. So, are you still on campus, Mallory? Are you in the lab? Are you dialing in from home? This is a pond. This is June Lake. Sorry, I'm fixing I'm saving the file that we collected. I've got to put a label on it somewhere. Hang on a second. Just want to look at that real quick. Trying to figure out what species we're looking at. It's not Coruscus. I don't know what this is. So, some little diatom. Probably Minutulus. Did you get your second vaccine shot, Mallory? Or is that coming up this week? Next week? Next week, right? I think you're like a couple of days behind Laura and those guys, right? This one is Caruscus. You can see it's got... Oh no, that one's not either. That's Hansia. Hansii. There's a bunch of different Stephanodiscus in the sample. I've got a little bit of pollen congestion right now. Barely noticeable, but when I went to drive my car yesterday, my windows are just coated with pollen, and I was like, I can't see. When I turned on my windshield wipers, it was just like a yellow blur. So I got out some like Windex and came out and tried to wipe all the pollen off of my car so that I could see. And after I cleaned off my windows, the paper towel was yellow. I mean, it had some dirt on it as well, but it was like yellow from pollen. And then, so that was yesterday. And then I came out again today, and my car was just covered with pollen again. Just one day later, not even a whole day later. Again, totally covered. So, I got these giant oak trees around my house that just produce a lot of pollen. This is an internal view of Lindavia intermedia, and it highlights a lot of the characteristics that are useful. So I thought I would just spend a second talking about what makes Lindavia Lindavia, and the different characteristics we can see in this sample. So these things on the outside edge right here are mantophotoportula. They have a central hole, and then satellite pores around them, which are these little slit-shaped things. They're triangular. If you were to look at them end on, they're triangular-shaped pores like these ones, because there's 3, and we can only see 2 because the third is underneath the central tube. And then between them, they have little openings. These are alveolar chambers right here. So you can see sort of like a chamber between each one of them. And if we were to look into the chamber, what we'd see is that the costi fork as they come through. That's a characteristic of the Bedanocoid Lindavias. And then this feature we can see on the valve face is the labiate process, or rhemoportula. And on Lindavia, it's always on the valve face. So you can see the valve face. Here's the shoulder, or the mantle junction, where the costi start to come off of the valve face, and it's inside of that ring. And then for this Lindavia, for intermedia, it has valve face photoportula as well. So these look basically the same as the ones that are on the side of the valve. They're central tubes with 3 satellite pores, and then you can also see some areoli with dome cribra. And the cribra you can see really clearly in here have a bunch of little sort of salt and pepper shaker opening type tops. And that's basically the characteristics for Lindavia. right here are all present. Not all Lindavia have areolae on the valve face, but this subgroup does. And they all have photoportula on the valve face, and also mantophotoportula. And in the case of the bedanocoids, they have triangular shaped satellite pores typically, so usually 3 openings. Mostly 3 openings. This one has sort of 2 rings of satellite pores. There's like a internal ring and an outside ring, but they're, only semi consistent, right? So sometimes there's only 1 in a row, sometimes there's 2 in a row. Probably size dependent partly. So could we make diatoms reproduce more quickly and absorb more carbon from the atmosphere? You can. It only helps if you sequester the carbon, though. So one of the things people forget is that, you could plant more trees. They're going to take up more carbon, but carbon dioxide. But when they reach sort of a maximum size, they don't grow very fast. And then the carbon that they take up doesn't really add much mass to the tree. And at night, when the plant grows, when they actually put the carbon onto their bodies and start to get bigger, they actually respire. So they breathe out carbon dioxide. They accumulate carbon dioxide when they're doing the photosynthesis, which basically turns it into sugar, and then they release carbon dioxide when they add it to their body mass. The same thing is true for algae. They will make sugars during the day when there's sunlight, and then use sugars mostly at night when when they're growing or multiplying. And so it's only really helpful if the carbon goes somewhere. And for algae, one of the nice things is that when the organism dies, the carbon gets buried typically. So it's not the blooms that are necessarily the best part. The part is that it actually gets buried somewhere. And you could get them to consume a little bit more carbon dioxide, but there's kind of a limit to how much they can consume, in part because the required nutrients for them, we'd have to pollute all of our water systems to basically get the algae to grow. And then find some way to quickly bury it as well might be challenging. So people have come up with ideas like this snooze, where they try to fertilize the ocean, for example, by adding nutrients to the ocean to try to get stuff to grow. And we're running sort of fertilization experiments as we dump a bunch of nutrients off the coast anyway. But, there's a limit to the amount of nutrients we can add to get things to stimulate growth. And it's going to wreck the water quality for other organisms. So, there's trade-offs associated with it that aren't necessarily good ones. Probably more promising than trying to get trees to do it. It's a lot easier to grow algae than it is to grow trees. So there's that. But still a bit of a challenge to get to do what we want, which is to reduce the total amount of carbon dioxide in the atmosphere. It's a solution. It's just not a great, simple solution like you might think it would be. And another consequence, of course, is to acquire the nutrients to do something like that costs a lot of carbon dioxide. It's like mining nutrients. Also requires us to use a bunch of fossil fuels, at least in our current sort of mode of operation. So it's a sort of a mixed bag, right? No matter what you do. Obviously, the better solution would be for us to try to limit our energy use or change our use of fossil fuels into something else. And that's also a challenge because of the way that we have energy demands. So, you know, it'd be great if we could just switch everything over to, you know, wind or solar, but right now, at least for where we are, those also require a lot of mining and minerals and resources that we don't have, and also political willpower that we don't seem to have, apparently. So there's a challenge to it regardless. You know, and you might use nuclear as a short-term stopgap solution, which I think is actually a good idea. But, you know, there's also some problems with that because for whatever reason, when we decided to invest in nuclear energy, we picked the wrong type. We should have picked the breeder reactors, but for some reason we chose the other type. And I guess because they were simpler, and it just became the standard that we used. And it's the dumb standard. Like, we should have picked the other one. Because it would have been a much better solution to use the breeder reactors. So our nuclear energy in the U.S., at least, as a solution, is the dumb one because it generates a lot of waste. It's a little more secure and a little simpler, but it's sort of the dumb solution. We should have picked the other form of nuclear energy. And if we're going to invest in it now, we basically have to, you know, develop breeder reactors kind of like they have in France. Which, again, I think would be a good idea. We need the political willpower. We need people invested in it. Interested in doing something about it is the most important part. So, in some cases, the most challenging part. Taking its time trying to figure this out. There we go. And then I'm just going to mess it up anyways because I wanted it on 7, not 10. Return to monkey. Bye, Mallory. Probably we could if we just return to monkey. Kind of fix the climate crisis. You know, the one of the positives out of the COVID crisis is that our carbon emissions actually dropped considerably as we became a little bit more isolated. It was noticeable, but it suggests that we could make a difference by changing our life habits a little bit. Also helps to have an administration that really wants to do something about climate crisis instead of one that just ignores it or refuses to acknowledge it. This is an external view of Lindavia intermedia. You can see a lot of the same features. The areolae, the openings on the valve face, and also the central photoportula are these dots in the center. And then this dot is the labiate process. There's two of them on this one. It's on a thickened rib, a costi right here. You can see in both sides of the valve that have a thickened rib. As the diatom gets, if we looked at a larger version of the same species, what we'd see is that the bigger the diameter, typically the more labiate processes they have. So they usually, when the really little ones, there's usually just one. And they get up to a certain size range, there's two. And then when they get to the next largest size up, they have three, and they're usually arranged in like triangular, like 120-degree differences. So they do some adjustments to the number of processes as they change their size. Stephanodiscus, Lindavia, we have a paper where we talk about the relationship between Stephanodiscus and Lindavia in June Lake. It's currently under review. So I'm hoping that we get some word on that relatively soon. I forget where we submitted it. But it looks at the long-term history from June Lake over the last couple thousand years, 3,000 years actually to be precise, 3,300. And it looks at the relationship between the amount of Stephanodiscus in the site and the amount of Lindavia in the site, and uses that to reconstruct lake stratification, which is actually kind of what I do as a paleolimnologist, is not just look at this stuff as pretty pictures or describe them as species, but actually try to apply them to past environments. Just want to see if I can fix some of the image quality a little. I feel like it could be better. And actually, I think maybe I want to see if the wobble needs adjusting at all. usually do that at the start of my stream, not at the end, but been unhappy with it for most of the stream, so if the sample is, if the wobble is correct on the sample, that dark circle in the background that's flashing will stay right where my cursor is. So you can actually, if you just stare at it, you can see it wobbles just the tiniest little bit, but it's actually pretty good. It's not moving very much. So that's not the issue. Let's see if I can... make an adjustment to the heating element. So it's getting close to 3 o'clock, which is probably where I'm going to end the stream. Got a nice, quiet lab stream from the SEM in the afternoon here. And I think what we'll do is, in the next 5 minutes, we'll probably give somebody a raid. Thank you for the follow, Snooze. And there was another follow in there. Oil Heap, thank you. One good one. Also, thank you for the follow. No Good Nick, about 45 minutes ago. Thank you for the follow. Cool Olds, thank you for the follow. And Dark Knight. And early on, Roger Twee. I guess that's Roger Twitch. And thank you guys all for the follows today. Just last week we were kind of closing in on 1600, and we're already closing in on 1700, so pretty good. I don't really have any sort of following goals, but it's always nice to have people here hanging out as we explore the world of diatoms in the scanning electron microscope. Take that picture. You love the stream? You live vicariously through my SEM? Well, I try to do a bit more streaming from the SEM coming up, either this weekend or next week particularly. I should have a bit more time. Next week is finals weeks here at Indiana State, and so I'm done teaching after Thursday. I have a class on Friday, which we're going to do some sort of a geocaching outdoor fun thing, hopefully. Which reminds me I need to stop and pick up some sort of goodies for the geocaching. And then Thursday I have a lecture And that's basically it for this semester. So my workload has just dropped off precipitously with respect to teaching. Yeah, hopefully I've never set up my own geocaching, but so I'm going to do a little bit of research later this afternoon, pick out some goodies for people, set up some sites around campus, and then let them loose. So should be a fun afternoon for my field geology class. Get them a chance to use their GPS a little bit, and maybe I'll put science-based questions inside the geocache. The finds, the cache themselves will have like science-based things that they have to answer. So should be a fun experience for my students. I just wanted the last day to be kind of like a fun day for them. Get them outside. Which reminds me, I should look to make sure that it's going to be nice on Friday. I've been really fortunate every day that I've had students go out. It's been really a nice day. It's raining here now, but Friday's supposed to be sunny and 70, so couldn't do much better than that, probably for Indiana. And maybe for everywhere. 70's about perfect for humans. It's a nice side view of Lindavia, and you can see the Mantiphotoportula, the little openings right here on the outside. You can see the areolae and central photoportula, and then also the labiate processes holes right there and right there. So all the same features we saw on the valve face on the inside and the outside we can see from this view, but you can see the Mantiphotoportula openings really easily on the outside here, which is why I stopped to take this picture. And I'm just going to find one more thing, and then I'm going to take a nice long picture of it, and I'm going to find somebody to raid, and I'll probably do a little goodbye for the day. It's been a fun stream, as usual. When I'm on the SEM, I'm in a good mood about it. Oh, it's in a Tusculus, Pseudotusculus or Tusculus, Anumastus. Let's see, maybe if we zoomed in on one of these epithemias. That one's not very promising. That's an interesting navicula. We've actually seen one very similar to this before that we imaged. They have TIE fighter striae. That's what we call those. Technical terms, lineolate striae. These ones look like TIE fighters because I think they're slightly dissolved. Really should put together like a stream over stream goodbye screen sort of thing. Should develop one of those. I mean, I have a starting screen every time. So I'm just setting up the image quality settings a little bit. I'm going to put it on a speed 8. I usually take it at 7, which is a 3-minute picture, but I'm going to set it to a 10-minute photo. And then we'll take that picture, and then just want to check the quality real quick. See if I agree with it, or if it agrees with me. think everything looks like it's in focus. A little bit higher resolution at 8 than it is at 7, and also I lowered the beam intensity down to 6. So we have a little bit higher resolved image here for a nice final image. It's looking good. Like to end on an 8 every time. It's good. I thank everybody for hanging out with me today. For Micah for doing a little bit of your job there as a moderator, and also for Mallory for visiting. All the follows, of course. And to let you know, we'll probably be back on the SEM maybe Saturday. I don't know. I think maybe we're not doing anything for the Spirit University stuff on Saturday this Saturday. I think it'll be on Sunday. So I might be able to come in and stream on Saturday from the SEM. If not, definitely Monday next week. I'll probably have a nice long stream from the SEM. And then Wednesday. But I will be back tonight from the light microscope. So I'm planning on doing a little late night stream, probably starting around 9:30 or 10. So yeah, lurking mostly is fine. You know, whatever happens in my channel that I need all the moderators for. Sometimes we get a bot. Occasionally we get somebody who, you know, says something lewd, I guess, but uncommon. So probably I'll stream a little bit tonight, and then I think I'm planning on just going straight into raiding Dell's channel, because I think he said he was going to do some microscope stuff after me. So hopefully we'll have a nice continuous late night stream starting around 9 or 10 and going right into Dell, carrying it into the late evening on the microscope. Sounds like fun anyway. And I think I'll do a little bit of prepared sample stuff from my light microscope, looking at some fossil diatoms and taking some pictures. And then I might put some of the live material on from the last couple of days. And then I think probably I'll also do a little bit of a water bear hunt before we go off to see Dell. So that's my plan. I think you're talking to Commander Shafard, right? All right, so let's see, who do I want to raid? I was thinking we would get Numb the Geek. It was his birthday on Friday, actually Thursday last week, and I like to torture him by making him play songs for me. So I also like to give him a raid and bring some people in over there. Let's set that up. Sounds like he's doing a live learn right now, actually. Oh no, he's doing a Radiohead song. All right, we'll check him out. He's one of my favorite musicians on Twitch. And thanks everybody for hanging out. We'll see you later today if you come back. Looking forward to that. From my light microscope later tonight. All right. Cool. Here we go.